Let's look at one application of matrices, and that is using their determinants to find the area of objects if we've transformed the coordinates of the objects into a matrix. So the idea is that the area of a parallelogram actually equals the absolute value of its determinant, the determinant that's formed by the coordinates in the XY system. One of the points of the parallelogram must be at the origin. Let's prove that idea informally in a graphical way. A more formal proof requires some knowledge of vectors, which we're going to get into later in the course. So what we're concentrating on here is trying to find the area of this purple parallelogram. And the parallelogram is really defined by 2 points, A comma C and B comma D. We have one point at the origin, we have these 2 points I just described, and then the point A plus B comma C plus D. And the reason this is A plus B comma C plus D, if you look at the distance along the x-axis of this rectangle, it is the distance of A, which is the x-coordinate of this first point, plus this distance B, which is the x-coordinate of the other corner. Because you can see these 2 blue triangles are mirror images of each other after rotation. Therefore, this entire distance along the x-axis is A plus B. In a similar way, the vertical distance of that entire rectangle is equal to C, the y-coordinate of this point, plus D, the y-coordinate of this point. If you put them on top of each other, you would get a vertical distance, a vertical height of C plus D. So if you agree that this distance is A plus B, the base, if you will, of this rectangle, the big rectangle on the outside, and C plus D is the height of this rectangle, is equal to base times height, or A plus B times C plus D. That's the area of the big rectangle. But we've got to subtract out a certain area to get that purple parallelogram area. So we're going to subtract out both of these blue triangles and both of the pink triangles, and when we're done, we're going to have the area of the parallelogram, the purple area. So thus the area of the parallelogram, the purple area, is equal to the area of the big rectangle, which we've already established is A plus B times C plus D, minus the areas of the pink triangles, minus the areas of the blue triangles. What we have left over will be the area of the parallelogram. So let's start out by finding the areas of those parts so that we can subtract them out. The area of the pink triangles, each of the pink triangles is 1/2 times base times height, and there are 2 of them. So we're going to have 2 times 1/2 times the base of the pink triangle, which is A plus B, times the height of the pink triangle, which is C. So when you simplify that, the 2 and the half cancel each other out, and we're left with A plus B times C, or the way I'm going to write it, AC plus BC, when you distribute that C to both terms. In a similar way, the areas of the blue triangles are 2 times 1/2 times base times height. In this case, the bases are vertical, and both blue triangles have a base of C plus D. Both blue triangles also have a height of B. So when you distribute that B to both terms, the 2 and the 1/2 cancel out, and you get BC plus BD. So these are the 2 areas we're going to subtract out from the area of the big rectangle to get what area is left over. So the area of the parallelogram, again, is the area of the big rectangle minus the areas of the pink triangles minus the area of the blue triangles. So if we substituted in what we know about them, we'd have A plus B times C plus D, minus the quantity AC plus BC, the area of the pink triangles, minus BC plus BD, the areas of the blue triangles. It's important that we distribute those negative signs to both terms in each of those parts. So when we distribute out this binomial here, we get AC plus AD plus BC plus BD for the area of the big rectangle. And then we distribute those negatives to these other terms. We have minus AC minus BC, minus BD minus BC minus BD. And some terms are going to cancel out here. The terms that cancel out are the AC minus AC, the BC minus BC, and the BD minus BD. Well, what does that leave us with? It leaves us with A times D minus B times C, which interestingly enough is the determinant formed by these 2 points if we put them into a matrix. So the reason for this was to give you some informal graphical proof of the statement we're about to make. So let's look at an example. We're going to find the area of a parallelogram formed by the point, the origin, and the points 2, 4, 6, 2, and 8, 6. It's helpful to plot them so that you can get a visual of what this looks like. So you could calculate the area using the standard formula for area of a parallelogram, base times height. But finding the base and the height is a little bit involved, and it involves use of the Pythagorean theorem and some trigonometry. This matrix method is a shortcut, provided that one of the vertices is at the origin or that you transform the parallelogram such that one of the vertices is at the origin. So we're going to go ahead and use this shortcut for this parallelogram. So the first thing you need to do is set up a matrix that involves the 2 real points that define the parallelogram. And in the more formal proof of this, these are actual vectors, the ends of vectors, but we're going to kind of simplify that at this point and just use the points. So we can set up a matrix with 2, 4. The x coordinates are in the first column, the y coordinates are in the second column, so 2, 4, and 6, 2. And the order actually doesn't matter because the area is going to be the absolute value, of course, because area can only be positive. So the area is the absolute value of the determinant of that matrix we just created with the 2 points. And you'll recall the determinant of a 2 by 2 matrix, the product of the main diagonal minus the product of this other diagonal. So it's 2 times 2 minus 6 times 4, which is a negative number, but we're taking the absolute value and it becomes positive 20 units squared. And that's actually a pretty fast way to determine the area of this parallelogram. However, you do have to make sure one of the vertices is at the origin. So let's try it on a parallelogram that involves some negative coordinates and is not fixed at the origin. So let's take a look at this parallelogram formed by negative 2, 2, negative 3, 6, 4, 1, and 3, 5. How do we find its area? Well, what we're going to have to do is actually translate, by shifting vertically and horizontally in this case, this parallelogram so one of the points is at the origin. The point I'm going to choose is the one that's closest to the origin, negative 2, 2, although it could work with any of the points. So what we're going to do is actually shift this thing over to the right 2 and down 2, meaning that we're going to add 2 to the x coordinates and subtract 2 from all the y coordinates. So I've graphically done this, but if you don't necessarily have to graph this. As long as you understand you're increasing all the x coordinates by 2 and decreasing all the y coordinates by 2. So this green parallelogram is the modified one I'm going to use for my area calculation in forming my matrix. So the matrix is going to be formed by these 2 points. So the matrix would have negative 1, 4 as one of its rows and 6, negative 1 as its other row. So the area of this parallelogram is going to be the absolute value of the determinant of that matrix we just formed, which is going to be negative 1 times negative 1 minus 6 times 4, which is 1 minus 24, or negative 23, the absolute value of which is 23 units. So the area of this parallelogram formed by those 4 points is 23 units squared. Now there are other methods of finding the area of a parallelogram, but oftentimes this is the fastest. So we've looked at an important application of the determinant, and that is determining the area of parallelograms rather quickly.